Okay, in this video I'm going to talk a little bit about the notation for our derivative notation and our notation for the integral. Our two biggest ideas in all of calculus, and we're going to be exploring the way these two interact really for the rest of the year. And also, so I want to start off by talking a little bit about the notation here and the fact that it actually does inform us about what's happening with the concept. Okay, so let's start off with the dy over dx. This is probably something you've heard me discuss in class before. But dy over dx, of course, the derivative, slope of a tangent. So if we take sort of our standard function, call it f, then if we want dy over dx, we're talking the slope at any point. So this whole idea here, okay, so of course if I want to find the slope of, let's say, that tangent, it doesn't look quite right, but you get the idea. What we do, and this goes back to the definition. Now, I will tell you that we do the definition of derivative. In this class, we actually don't do the derivative, the definition of the integral, okay? Now, we work through this algebraically, but the concept is what I'm interested in today. Basically, if we want the slope of this tangent line, we take 2 points and then we slide them infinitely close, right? And we do that whole process of the limit as h goes to 0, etc. Today we're just going to think about this in the context of the notation. So if you think of this as a little slope triangle, okay, then this is our rise and this is our run. Now, instead of calling this delta y over delta x, we call this dy. And the reason why we call that rise dy is that means an infinitesimally small change in y, okay? So infinitesimal is really, if you think of it as the reciprocal of infinity, infinitesimal. So there's no number that's closest to 0. But if there was such a thing, that's how we would think of dy. So we get as close as we can. This is the limit process. So the limit is the engine that makes both of these things work. So basically, dy is essentially the same as taking delta y and limiting it to 0. And then here is dx. So dx is an infinitesimally small change in x, and the same thing. We basically think about delta x, and we're limiting that to 0. Thus, we take those 2 points and slide them infinitely close, getting our derivative. So the concept of the integral is similar. We're going to use calculus. So we start with a to b. Okay, let's talk about f of x as a positive. It's just a little bit simpler. We have our function here, okay? And we've been doing these types of things, even though this notation is new, we've been finding areas under the curve actually going back to pre-calculus. So the way we've done it up until now is we approximated. Oh, let me make the point that just remember that if we approximate the slope of a tangent line, we can choose two very, very close points. The same is true for approximating area under the curve. Oh, sorry, not a very straight line. But one of the more common ways we did was rectangles. I know we also use trapezoids here, but today we're going to just be using rectangles when we talk about the concept of the integral. So, if I look at this, this looks like, let's see, how many rectangles are there? 1, 2, 3, 4, 5, 6, 7 rectangles. Okay. So if I look at that curve, and if I was approximating the area under the curve using those 7 rectangles, it doesn't look like a bad approximation. But one of the things we think about is, just like to get a better approximation here, we would move those 2 points closer and closer together. Here, to get more and more rectangles would give us a better approximation. So let's say I said, okay, so this is a right Riemann approximation. I use 7 rectangles. This approximation is good, but it's not good enough. What could we do? Well, we could go to 10 rectangles. We could go to 20 rectangles. We could go to 100 rectangles, et cetera, et cetera, et cetera. So hopefully you see where this is going. So essentially, if you think of each one of these rectangles as having a width of delta x and a height of f of x, right? Really what we're talking about doing is just like we did over here, we're taking delta x and we're limiting that to 0, right? So just like we limited both dy and dx to 0, we're limiting delta x to 0 here. And once again, we have a name for that. we would call that dx. So the idea that we see in this notation, when you see this f of x dx, this would be the height of one of our rectangles, and dx would be the width. And the one thing we have to understand about this is we're actually going to slice this up an infinite number of times, right? So essentially the number of rectangles, call it n, is going to infinity. And each one of these infinitely thin rectangles will have a height of f of x based on this curve. Okay, so when I actually look at this notation, don't forget that it means the f of x is the height, the width is dx, we start at A and we finish at B. If the area is above, we're going to add that. The area below, we're going to subtract. And that's where that notation comes from. And both of these are sort of fueled by limits. Okay, I just wanted to talk briefly about that notation today. That's it for this video. Yeah, that's it.